Hello guys, this is the first video where we will actually perform some system identification, and we will perform identification of linear models in this video. So a general system of ODEs can be written on the form we have here on top, where x is the state and x dot is the time derivative of x. U is some input and y is some typically measured output. And if this function f here is linear, then we can write that system of equations on this form here. So this is sometimes referred to as a linear state space model, where we have the dynamics matrix A and the input matrix B. And estimation of this model then means that given some data, y and u, find good parameters for A, B, C, and D. All right. Before we can do that, we note that computers often work in discrete time, and data sets are always sampled in discrete time points. So a continuous time system has infinitely many points here in time. The state evolves continuously, but the data is only available at certain time points when we have recorded the data. And quite commonly we sample, so take a measurement at a fixed time interval. So when we estimate the model of this system, it's often easier, at least for linear systems, to estimate a discrete time model. So that is a model that relates the state at a particular time index k to the state at a particular time index in the future, k+1 perhaps. So even though maybe we might be interested in this model here in continuous time, where we have a relation between the derivative of the state and the state, it's much easier to actually estimate the discrete time model that relates the state at the current time point to the state at a particular time point in the future. All right, so there is some kind of mapping that takes this continuous time model into a discrete time model. And that mapping is essentially integration. So if we simulate this system here from a particular point in time forward to the next point in time here where we have data, that implies integration, right? We're integrating this differential equation. So this would be in code perhaps called an ODE integrator or a differential equation solver. So when we actually estimate this discrete time model, we actually estimate something that is a function of both the physics and the integration of that physics. All right. So how is that performed? Yeah, so we call the transformation of a continuous time system to a discrete time system, we call that discretization. And the discrete time model then typically goes from one time step or one time index k to the next time index k+1. And the difference in real time between k and k+1 is this sample time, so the duration of time that passes between two samples. And for linear systems, if the input signal u is piecewise constant, then we can actually perform this discretization exactly without any approximation error. And for linear systems, the inverse map also exists. So if we have estimated a discrete time model, we can actually convert that into a continuous time model. So that's good to keep in mind. But when we use the model, very often we use the discrete time model anyway. So it's not a problem that we estimated it in discrete time. All right. So the very most simple form of a linear model is perhaps something like this. So here we don't even consider any state at the moment. We just consider inputs and outputs. So we say here that the output in the next time point, k+1, is some linear combination of previous outputs plus some linear combination of previous inputs. So here a0 is some numerical coefficient that we don't know yet. We want to figure that out. And we can have any number of past outputs and past inputs here to build our model. And this is typically called an autoregressive model with external input, so ARX. And we note that this can be written as a discrete time transfer function with two polynomials in the z variable here. So if we perform the z transform of this model, we arrive at this discrete time transfer function. And if you don't know what the transfer function is, that's all right. But we note that any transfer function that is at least proper has a realization as a state space model. So we can convert this transfer function to a state space system if we want, like the ones we saw on the first slide. All right, so how do we estimate such a model? Here the model is trying to predict the output at the next time instant as a function, linear function of past outputs and inputs. So if we take a bunch of outputs here, here is the output at time 3, output at time 4, and so on. We note that given the model here, say that we only have 2 past outputs and 2 past inputs in our model. Then y3 is given by this little short expression here, and y4 is given by a very similar expression, but all signals are shifted 1 step in time, and so on. We note here that this could be written on matrix vector form. So here we collect all these left-hand side outputs in the future y vector, so this boldface y is now a vector. And we collect all the past outputs and inputs in a matrix phi, and we collect all the parameters, so the a0, a1, b0, b1 into the w vector here. Then we can write it on this form. Y is now phi times w, all right? So this is just matrix notation for this expression here, but it is equivalent to this model we had up here. All right, so how do we estimate that? We can estimate it, for instance, using least squares estimation. So if we say that we want to minimize the squared difference between our measured values, y, and our predicted values, so this would be the output of the model, y hat. I usually use a hat for an estimate, so an estimate of the output in this case. If we want to minimize this with respect to the model parameters w, we can write that on this form in matrix notation. So minimize with respect to w, the 2 norm square of this matrix expression. All right, and linear least squares has a nice closed form solution. It's given by this pseudo inverse times the future y vector here. So we can compute these parameters a0, a1, and so on in closed form. But in practice, we don't actually form this pseudo inverse because that's a bit expensive and also numerically perhaps not optimal. But this is such a common problem to solve that in Julia there is actually a shorthand. So if we have a matrix phi and we have the y future vector here, we just say phi backslash yf, and that will solve this particular problem, but in a numerically more efficient and robust way. All right, so that's very easy to do. And now let's do this in practice. So this environment I'm in here is called a Pluto notebook, similar to a Jupyter notebook, but reactive. And this is running on JuliaHub, and this notebook is available for you to run as well for free if you want to follow along. And to do that, you go to JuliaHub.com and you log in by clicking at the little figure here. You can create an account, it's free. Then you click on Notebooks here in the left-hand side menu, and you go to My User. I have a number of public notebooks, so my user is Frederick Carlson 2 here. And in my folder System Identification, you find this notebook, Identification Video 2. And if you click on that, you will get to this notebook. All right, so to start doing something in practice here, we load the package Control System Identification. We load some additional control systems related packages, a plotting package, and a package that contains some interactive elements for this notebook. All right. So here I have some data, y and u. I have simulated this data, so I know the exact system that has produced the data. So that's obviously unrealistic. If you have collected data from a robot out in your lab, you don't have that luxury, but I have that luxury here. We see we have along vector y, there is 100 samples, and we have u, also 100 samples, and we can plot it here. So here we see y on top and u in the bottom. All right, so now we would like to find a model that fits this data, and we're going to attempt a linear model. So to form this matrices phi and the vector of future outputs y future, we have a little function called getARXregressor that exists in this control system identification package. And just to show how that works and what it gives you, I create a number of symbolic variables here. So here I create a symbolic y vector of length 13 and 1 for the input, and then I pass them into the ARXregressor function here. And that function returns us the following two things. So it returns us the future y's, and it returns to us the phi matrix. And here we see that to predict, so this is shown as a row vector, but it's actually a column vector like this. So we see that the first future output is y3, and that is a function of y2 and y1 and u2 and u1. So we see that we only use past information to predict the future. And then we slide the time index forward. So to predict the output number 4, we use the output number 3 and 2, and so on. All right. So if we pass our data into this getARXregressor, we will actually obtain the phi regressor matrix that we need. And here I have two sliders that allow me to select how many past outputs do I make use of, how many A coefficients, and how many past inputs. So if I increase that, we see that now I use 5 past outputs. So to predict the 6th output, I use output 5, 4, 3, and so on, right? And we can do the same with U there, add more U variables. All right, but we're gonna try with 2 of each, 2 past outputs and 2 past inputs. All right. So here we see what is returned by this function. We have a long vector of future outputs. We see that it's of length 100 minus the number of past outputs. So we can't, of course, we must split the data so that we have a distinction between past and future. And we only have 98 future values available if we have used 2 values in the past. All right, and here is our phi matrix. It's also 98 elements tall, but it's 4 elements wide. All right, so to now form the estimate of the A and B coefficients, we just call this backslash operator. So that will perform the least squares estimation for us. And then we see it returns a vector of 4 numbers. All right. So we can immediately now actually use this model to predict the output. So here I form an estimate, what the model thinks of the output, and that is now just this simple equation phi times w that we had above. And we can plot that. So now we plot the data versus the prediction, and we see that they look similar but not identical. In particular, we see that the model prediction kind of lags behind the data, so that's some cause of concern perhaps. But for now it looks fairly good. So now each point here in the model prediction is a function of the 2 previous outputs and inputs. We don't show the inputs here, but they are behind the scenes. All right, so are we happy with this result? Should we perhaps use more past inputs and outputs? Yeah, who knows? Let's see, let's validate this model slightly. To validate it, we actually make use of the built-in function ARX. So here we performed this estimation by ourselves. We created the regressor matrix, we performed the least squares estimation and performed the prediction. But there is a built-in function that does all of this for you and packages that into a structure, a model structure that we can use. So to use that function, we first package our data, y and u, into an identification data input. And that structure actually wants the transpose of the data matrices here. And we provide the sample time. We sample this data at every 0.1 seconds. So now we have an input-output data object, and we pass that into the ARX function. And that function also needs to know how many A coefficients and how many B coefficients do you want. And it returns to us a model in the form of a transfer function. It says it's a transfer function and it's discrete, and here is the polynomials. And we can see that these polynomials match the vector of coefficients we estimated manually. So this 1.1 here appears here, and this 0.005, it appears here, and so on. All right. So now we can say there is a function called simplot. It plots the data and it simulates this model forward in time. And we see how well that works. And we see that, in fact, it doesn't work very well at all. It's a terrible fit. It says here 5% fit. Okay, so what went wrong here? What's the difference between this simulation and the prediction we showed up here that looked very good? All right, here to form each predicted value, we just looked at the two previous values of the output. All right, but here in the simulation plot, we don't have access to the data along the trajectory. Instead, we use the input and predict an output, and then we feed the output of the model back into the model again. So it's an auto-regressive model, right? And we do that forward in time. And then we see that over a long horizon, it doesn't actually fit very well at all. So this, I would say that this model fit is quite bad. Okay, so what's the problem here? Let's see. First here I show the true system that generated the data. So since I simulated the data, I have access to the true system. We can compare that to the model we estimated. And we see that the numerator polynomial is quite far off, right? Actually, the coefficients are perhaps not too far off, but the denominator polynomial is very far off. Here we have 1.97 and here we have 1.1. And this value is also very far off. So we haven't actually found the true coefficients for this linear system, even though our model order was correct. We had 2 B coefficients and 2 A coefficients. So somehow we have failed. All right, and let's try and figure out why we have failed. Here I show a Bode plot of the true system and the estimated model, and we see that they don't agree very well. Okay, so maybe the problem is just that we didn't have enough data. Maybe if we increase the amount of data, we will get a better result. So here I have a slider that allows us to increase the number of data. We used 100 data points. What if we use 1,000 data points? See, it still doesn't look very good. The Bode plot still doesn't capture the resonance peak here. And if we increase it to 10,000 data points, we see that we have a terrible fit. And our estimated model here in the Bode plot still doesn't capture the resonance peak. So it looks like it doesn't matter how much data we use, we're still not going to capture the true model. All right, so there is some problem with this way of estimating the model. Let's see if I can get rid of the presentation mode. All right, sorry about the scrolling. Okay. So it comes down to the consistency of an ARX model under different forms of measurement noise or disturbances. So this ARX model and the estimation we used here, it's consistent. And what does consistent mean? It means that as we get more data, we will have a vanishing bias and a vanishing variance. Okay, so this is consistent if we have the following system generating the data. Okay, so here we have a polynomial in the Z transform variable, and here we have the Z transform of the output, the B polynomial, and the Z transform of the input, and here is a Z transform of the disturbances. So epsilon here is expected to be Gaussian white noise. All right, so this can be rewritten into this form, and here we see that we have the A polynomial in the numerator multiplying the residuals. All right, but that's not how I generated the data. Instead, I simulated data from the system without noise, and then I added noise after the simulation, so just measurement noise. So the ARX model expects data on this form, but I provided it data on this form, and the difference here is that the noise is not filtered through the A polynomial here. And if we have this mismatch, if we have measurement noise when we estimate this ARX model, we will never find the true estimate, the true model. We will always have a bias. All right, So that's slightly problematic. So even though we're in this beautiful case of the true system actually being linear, we still failed at finding the true coefficients of the system. In practice, of course, the system is probably not linear, so finding the true coefficients doesn't really make sense anyway. But here it would actually make sense, and we still failed. All right. So what can we do to make this ARX model consistent? All right. So the problem here was that we have some errors not only in the thing we're trying to predict, but also the regressor we are using to predict the output. This phi is comprised out of measurements, right? We put the past measurements, past output in this phi matrix. So if there is a measurement noise, this one will also have errors. And there is a way to actually account for that, and it's sometimes called errors in variable regression, otherwise known as total least squares. So we can actually estimate this model using total least squares instead. And it's not too difficult to do that. Let's see, I've hidden the code. We still call the same ARX function, but now we say the estimator is total least squares instead of least squares. And when we do that, we obtain this green transfer function instead. So we see with 100 data points, we capture the resonance, but it's off in magnitude, right? And the phase curve looks much closer. And if we simulate here now, we see that the green simulation of the ARX model looks much better than what we had before. And if we increase the number of data points again to 1000 here, we see that now the total least squares model is very accurately capturing the true system. And the same in simulation here. Now we have a 95% fit. And remember, there is some measurement noise, so we will never have a 100% fit. All right, so in this case, it was quite simple to actually improve the estimate. Another way to make ARX consistent is to just vastly increase the model order. And we can do that. So I have these sliders up here. Sorry for the scrolling. I will bring them down so we can manipulate the number of coefficients. So if we now increase the model order, we see that this orange curve will go from a fairly poor fit to hopefully slightly better. So now I'm increasing the order of the A polynomial, the number of A coefficients. And now maybe I'm increasing also the number of B coefficients. And we see after a while we have a fairly decent fit here. So we could somehow compensate for the fact that the ARX method is biased in the presence of measurement noise by simply increasing the model order. And we see that now both the least squares and the total least squares fit. They are roughly equally good here. All right, the next little section here is on uncertainty quantification. So if we have some kind of statistical model here, so we say that y, the output, is some regressor times a coefficient vector plus some normally distributed noise here, epsilon. And we form our estimate of the coefficient w hat as this kind of closed form solution with a pseudo inverse. Then we can see that this estimate is equal to the true parameter here plus some term that depends on the noise. So if we compute the expectation of this term here, we see that this is the in expectation is equal to the true value, provided that the noise is uncorrelated to the regressors. And if we remember, that's not actually the case in this situation where we have simulated here. So there is some measurement noise here inside the regressors also, so this doesn't actually hold. But if it would hold, if the noise was indeed uncorrelated with the regressors, then we could make use of this estimate and we would have a consistent estimate, meaning that there is no bias. If we look at the variance that is given by this expression here, so the variance of the estimation error, we can just plug in the values we had here and we arrive at an expression that includes the regressor. This is called a Gram matrix times the variance of the noise. And if the number of data points goes to infinity, then this term becomes very large. And since it's the inverse, this goes to 0. So together with the zero bias up here, this proves that the estimate is consistent, provided that we don't have this correlation between the noise and the regressor. All right, so I have a warning here that it's not always the case that the noise is uncorrelated with the regressors, and if that doesn't hold, then this estimate of the variance is incorrect, so then we shouldn't actually make use of that. All right, so in summary, estimating discrete time transfer functions is very straightforward using the ARX methods. There are some pros of this method. The solution is available on closed form, so you don't need to run an iteration like gradient descent or anything. That also makes it extremely fast and numerically stable. It takes milliseconds to estimate this. It's easy to extend to cases where you have the noise has unequal variance, or maybe you want to apply some frequency weighting to the estimate. That's possible. You can also add nonlinear regressors as long as the model is linear in the parameters. You can solve the least squares problem in closed form. The drawbacks is that the ARX method is slightly short-sighted, and what I mean with that is that it only considers the immediate past when it predicts the future. And it only predicts one step into the future. It doesn't care about the long-term consequences about the prediction. And that is oftentimes a drawback, but it can actually be a benefit also sometimes. Maybe you don't actually care about what happens long time into the future because you have a PI controller that will make sure that you suppress any slow moving kind of low frequency disturbances. And in that case, maybe it's okay to have a model that is incorrect for low frequencies, but okay for higher frequencies. And another drawback is that you might need a high model order if you have disturbances to capture those. All right, thank you.